Hello everyone. Thanks to everyone for watching this video. My name is Qi. I am an architect and engineer. Today's video is titled Behavior of Beam Columns, and it is going to provide you a broad overview of beam columns and also the elastic analysis of beam columns. I am going to give you an overview of what I am covering in today's video. First at all, we will have a look at some fundamentals of the behavior of beam columns, then move on to the mathematical derivation, then wrap up with conclusions. Theoretically, all structural members may be regarded as beam columns. Beam columns may act as if isolated, as in the case of eccentrically loaded compression members with simple end connections, or they may form part of a rigid frame. It is convenient to discuss the behavior of isolated beam columns under the three separate headings of in-plane behavior, flexural torsional buckling, and biaxial bending. When a beam column is bent about its weaker principal axis, or when it is prevented from deflecting laterally while being bent about its stronger principal axis, as shown in Figure A. Its action is confined to the plane of bending. This in-plane behavior is related to the bending of beams and to the buckling of compression members. When a beam column which is bent about its stronger principal axis is not restrained laterally, as shown in Figure B, it may buckle prematurely out of the plane of bending by deflecting laterally and twisting. This action is related to the flexural torsional buckling of beams. However, more generally, a beam column may be bent about both principal axes, as shown in Figure C. This biaxial bending, which commonly occurs in three-dimensional rigid frames, involves interactions of beam bending and twisting with beam and column buckling. In this video, the in-plane behavior of isolated beam columns will be discussed. Next, we will introduce the elastic beam columns. When the deformations of an isolated beam column are confined to the plane of bending, its behavior shows an interaction between beam bending and compression member buckling, as indicated in Figure B. Curve 1 of this figure shows the linear behavior of an elastic beam, while Curve 6 shows the limiting behavior of a rigid plastic beam at the full plastic moment MPL. Curve 2 shows the transmission of a real elastic plastic beam from Curve 1 to Curve 6. The elastic buckling of a concentrically loaded compression member at its elastic buckling load NCRY is shown by Curve 4. Curve 3 shows the interaction between bending and buckling in an elastic member, and allows for the additional moment N times delta exerted by the axial load. Curve 7 shows the interaction between the bending moment and axial force, which causes the member to become fully plastic. This curve allows for reduction from the full plastic moment MPL to MPLR caused by the axial load, and for the additional moment N times delta. The actual behavior of a beam column is shown by Curve 5, which provides a transmission from Curve 3 for an elastic member to Curve 7 for full plasticity. Next, we will introduce the elastic beam columns. A beam column is shown in Figure A, which is acted on by axial forces N and end moments M and beta M times M, where beta M can have any value between -1 single curvature bending and +1 double curvature bending. For isolated beam columns, these end moments are independent of the deflections and have no effect on the elastic buckling load NCRY. The beam column is prevented from bending about the minor axis out of the plane of the end moments, and is assumed to be straight before loading. The bending moment in the beam column shown in this figure is the sum of the moment due to the end moments and the reactions, and the moment n times w due to the deflection w. Thus, the differential equation of bending is obtained by equating this bending moment to the internal moment of resistance. The solution of this equation, which satisfies the support conditions WO equal to WL equal to 0, is given by this equation. The bending moment distribution can be obtained by substituting W expression into the differential equilibrium equation. The maximum bending moment can be determined by solving this condition. For the position x max of the maximum moment, whence this expression obtained, the value of x max is positive, while beta m less than this expression. And the maximum moment obtained by substituting equation for the position x max expression into the differential equation is given by this equation. When beta m larger than this expression, x max is negative, in which case the maximum moment in the beam column is the end moment m at x equal to 0, whence m max equal to m. For beam columns which are bent in single curvature by equal and opposite end moments, beta m equal to -1, x equation for the deflected shape simplifies, and the central deflection delta max can be expressed non-dimensionally as this expression, in which delta equal to m times L squared over 8 times EIY is the value of delta max when n equal to 0. The maximum moment occurs at the center of the beam column and is given by this equation. These equations are shown non-dimensionally in this figure. The figure shows the variations of m max over m with the axial load into n over NCRY and the end moment ratio beta m. In general, m max remains equal to m for low values of n over NCRY, but increases later. The values of n over NCRY at which m max begins to increase above m is lowest for beta m equal to -1, uniform bending, and increases with increasing beta m. Once m max departs from m, it increases slowly at first, then more rapidly, and reaches very high values as n approaches the column buckling load NCRY. From conclusions, what we learned: beam columns are structural members which combine the beam function of transmitting transverse axial forces. In-plane behavior of beam columns is related to the bending of beams and to the buckling of compression members. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.